Ladies and gentlemen, ladies for those who are watching it on YouTube at some point in time, welcome to our third lecture on Bayesian data analytics. And today we will cover the aspects of actual computation of expectations, because I think it will be better. Actually, what we will be doing here, we won't be straight focusing on Bayesian stuff, but we will generally assume that we have a distribution that we want to compute an expectation of. And for that, we will have to do some work in order to get to that result. Because expectation of because generally expectation is what we really want. Did I just turn off the recording by an accident? Just to be sure. And no. Okay, that will have to be edited out, I think. Okay, it's still recording. Okay. Fortunately, we have a power of editing later, so there won't be an issue. Okay, so generally, in what we want in probabilistic computation is to compute an expectation of certain function of parameters. It might be the expected value of parameter, but it might be an expected value of certain functions of multiple parameters. This is actually very broad field because we are computing the expected value of a function. It covers actually all kind of functions all kinds of statistics that we really want. It can be quantiles, it can be medians. In histogram is always an expectation. So we have about multiple things that we want to compute, and moreover, expected value is generally a very good estimator. Because expected value of posterior distribution is a very good quantification of what we want. So, because expectations that we want, so what we really want is to having a function of our vector parameters q, general vector parameters. It might be a single parameter, it might be a vector parameters. Which has a probability distribution, P of Q. We want to compute an expectation function, which is generally an integral over the entire space of possible values of Q that the probability distribution is defined on. And so it will be like generally averaging of the function here over the probability distribution. That's the expectation. In discrete case, it's of course much simple because we don't have an integration, we are summing. If Q has discrete available values, we just need to compute the expectation this way. So how to get that expectation? Because obviously, integration is not what we really want. Analytically, integration of anything more complicated than a polynomial is a problem. Numerically also, but we'll cover that in a second. So, how to get to a way that we can in some way estimate this expectation of this function? And for that point, the popular idea would be a model estimator. Model estimator is an idea that we find the maximum of the posterior, and as we can made it similar to a Gaussian distribution. If Gaussian distribution, we know that expected value of Gaussian distribution is in the maximum of this distribution, right? So using that, we could numerically compute the maximum value of posterior distribution, which is of course relatively simple because we have numerical algorithm for optimization. They can find this maximum, and as long as this function is well behaved, there will be no problem. If the distribution is not very skewed, then the maximum is close to the expected value. So that's this. Unfortunately, larger skewness, larger problem. If the function is far away, if the optimum is far away from the expected value, no, well, then there's a problem that it will be just a poor estimator. So generally, we have two problems here, or three even. First, skewed distributions are problematic. We do not have any uncertainty quantization from such estimate of the expected value, and of course there will be issues with multimodality. If you remember, we discussed last time about distribution of salaries in Poland. It's a multimodal distribution. The first maximum is well below the expected value, so or the mean. So that's the main issue. So it doesn't mean that a model value is useless. It can be useless because, for example, knowing that a maximum of distribution of salaries is located around 2,000 zloty is something that's an important information. But it does not solve the problems of computation. That's why generally more advanced methods are needed. Maximum theory is used, for example, it's used in machine learning with Gaussian processes, which are a kind of Bayesian model but with simplified computation. So it is useful, but it is very limited. Different or certain extension of the idea of model distribution is Laplace approximation. Laplace approximation is generally a very simple idea that is present all over the entire numerical optimization, numerical methods. How to replace the problem you have with a simple problem. So create a model of your problem. So you've seen it in automatic control through linearization. You've seen it in numerical optimization through Newton's method, creating a quadratic form approximation of function. It was in the numerical methods generally to replacing the problem with a linear or quadratic. In this case, the idea is to create a Taylor expansion around the mode of the logarithm of probability distribution. So we take the logarithm of probability distribution, and around the maximum Q star, we create the Taylor expansion. It creates us the value of the function, then it should include a gradient multiplied by the distance from Q star, but we are in the maximum, so the gradient is equal to 0. So this part is not here. And finally, the second derivative, the Hessian matrix, which is a quadratic matrix of quadratic symmetric matrix of partial derivatives of the probability distribution with respect to all the elements of Q. And we denote this as h of Q star because we evaluate the Hessian at Q star. So this creates a model, quadratic model, as a quadratic form of this logarithm of this vector, of this scalar function with vector argument. Because, again, probability distribution takes values from 0 to 1, so its so its logarithm will have this form. Having that, we can create the approximation of the density. Why? Because if we want to switch again from the logarithm to the density function, we just need to exponentiate it. If we exponentiate this quadratic expansion, we get something proportional to the exponent of quadratic form on the matrix of h of Q star. Why proportional? Because we have those parts that are with drops, and we have the value of logarithm of p of q star is when exponentiated, this sum will be a product. So this will be a constant which can generally ignore. So it will be a proportional to a certain normal distribution with expected value of q star, and covariance matrix being an inverse of the Hessian, because that's how normal distribution are. And then we can compute the expectation using Gaussian integrals. And Gaussian integrals are generally computable, especially in low dimensions, because there are formulas or algorithms to compute them. So we can then just averaging it over normal distribution will be much, much simpler. So that's the general idea. So the approximation will kind of give us some way of quantizing the uncertainty and some similarity to others. Of course, the more complicated distribution, the approximation by Gaussian will be limited. However, the Laplace approximation has multiple uses. For example, in simpler distribution, there is an idea, there's an entire class of course so-called latent Gaussian models, we'll maybe mention it later during the course, where we can easily create Laplace approximation of marginal distributions there. And then it works very well and very fast. It reduces all the problems with computation, even in large dimensions. So this is a very useful case. So that's that. We now need to move to, so as we see, the model approximate, we can get as much as from mode as we can, either through just finding a mode and or creating its quadratic approximation. So we need a Hessian. That might be a complicated computation or not, but it still is limited. Other option is, of course, compute the integrals directly. And this is a situation like this. Generally, in one dimension, computation of integrals is very simple. Because quadratures, so numerical computation of integrals, is a well understood problem for scalar functions. Especially for bounded intervals, we have a very good quadrature selections based on either interpolation, so kind of interpolation quadratures, even from simple Euler quadrature, which is the simplest way, to using appropriate selection of nodes, we can even go to Gaussian quadratures of different types. So like Gauss-Legendre, Klein-Curtis, Gauss-Lobato, and other stuff, which are very efficient methods of integration. The smaller the function is, the integration will be better. And they can be really fast evaluated. Those computations can be really fast, and of course we can also use some kind of adaptive quadratures, which are even more efficient because they split the interval into parts where more happens and less happens, and high order of correctness is obtained. So for bounded intervals it's great. For unbounded intervals, it's not that good because we have two options. First option is to use some kind of transformation, like for example, logistic function or some other, which will transform our unbounded interval that we are interested in integration. So for example, a real axis into some bounded interval, and then use some kind of quadrature from bounded interval. And this is the problem which happens in details, because those values from infinity will be compressed to something. And those compressions can be problematic, because they can really lose the... if you don't control what's happening, there will be some changes, which might or might not be. Other way is to compute those through dedicated Gaussian quadratures for unbounded intervals. Those are generally Gauss-Hermite for minus plus infinity interval and Gauss-Legendre for 0 plus infinity interval. And the issue generally those quadratures on bounded intervals work like this. Approximate the function using polynomials. From those polynomials, compute integral of the polynomial, and you're done. In case of, for unbounded intervals, you want to approximate the function with a sum of functions that are products of polynomials, and in case of Gauss-Hermite, it will be Gaussians, and in case of Gauss-Legendre, it will be exponential functions. The issue is that while any continuous function on bounded interval can be very well approximated with polynomials, we don't know how high order, but we can find an approximation of any arbitrary order. Representation of function on unbounded interval with exponents is not necessarily as good defined. Formally, of course, there is an series. If the function is square integrable, there exists the series expansion. But this series it might be very difficult to find appropriate level at which we need to end the series, and unfortunately, those quadratures, especially Gauss-Legendre quadrature, are terribly bad conditioned when computing high-order quadratures. When you get over like order 10 or 7 or like 10, 15, then numerical issues in computing the quadrature nodes is so high that there are problems. So that's the issues that we have with using those quadratures. But like generally, the problem is, let's say, well understood. What with higher dimensions? And here problems start, because generally you have to define grids, and those grids can be used in order to compute those integrals. I'm not sure that you can see the grid here, but generally only those those squares that are containing a bit of our curve are influencing the integral. The more here and here will be less. Maybe we can close the window if you're cold. The more values we compute outside of it, the most useful situation. And the issue is that the probability density function that is in the integral always integrates to 1, right? So if it integrates to 1, there will be places where it will be very, very small. So it will not contribute to the computation. And the more difficult geometry will be, we will evaluate values on multiple points on the grid and do not influence the computation. And here it is very small. It is a two-dimensional case. What will happen in higher dimensions? How this computation will really work? And that requires for us to think about what contributes to the expectation function. Because our expectation is an integral, of course. And in our intuition, when the probability density is large, right, then the function, the integral should, those parts should contribute most to the integral, right? Especially that this integrates itself to 1, right? So the closer we are to the maximum, the better approximation we should get, right? So the contribution of the probability distribution to the expectation is the strongest near the maximum, and the farther away it is the contribution is less. But integration is, especially in multiple dimensions, does not only rely on the aspect of those values, because the maximum is an isolated point with some neighborhood, right? So if we have a simple interval, we know that somewhere here is the maximum, and the entire area of integration, there will be those tails that are not that important, right? However, in two-dimensional case, there we just took a 1/3 of the volume for our computation. Here, in two-dimensional case, we have in both sides and also the corners. So we have we have 1/9 of the entire volume that is located around the maximum. So the values around the maximum are still the biggest, but the area where the function is small, where it exists, is becoming much larger than the area than the maximum. So the maximum area will be multiplied by 1/9, and the rest will be the 8/9. In case of three-dimensional, then we have 1/27 of the entire computation, right? Because we not only have neighbors in one axis, but also above and below. So the contribution of the part around the maximum will be balanced by a lot of volume happening around it. And dimensions are growing and growing, because in probability models we will often have more than 3 dimensions. We can have dozens or hundreds of parameters which we have to handle, and each of them adds to the dimension of the probability distribution. So the neighborhood of the mode, so the highest values of probability density functions, won't be contributing that much, because generally the further we get from the mode, the more volume we have available, right? If we are in a ball in the middle, there's a small point here, like the center of gravity, but the volume around it also is becoming larger. So the larger the space, the less part of the integration happens here. So actually, the computation here, the multiplication, distribution times the times the volume part, so the dq part, which you usually ignore when we think about integrals, in multiple dimensions we have to think about it. So this part, the main contribution will be far away from the maximum. It will be somewhere, areas where function is still noticeable, but more volume is happening. Enough volume that it will be balanced. And further away, because still our probability density function has to integrate to 0, to 1, those values will be negligible. But there will be an area where there is the most contribution to the expectation. As this area is called the typical set. The typical set is a set where generally most probability lies. Because it is kind of a fuzzy surface that we cannot define explicitly as a shape in the space. This shape will be, let's say, it's more you can tell as a cloud of samples from the distribution. So this is located progressively farther away from the mode the higher dimension is, because the volume will grow rapidly. It will grow exponentially. So the volume grows exponentially and it's multiplied by the distribution. So the volume around the mode will be small, and the mode around the typical set will be large enough that even the smaller values of the function multiplied by that volume will generate us the most probability. So generally it can be shown with certain mathematical analysis done with the increase of the dimension, entirety of probability will be located in the typical set. So this is absolutely counterintuitive to what we think about integrals normally, because we normally think about integrals as integrals of one variable, so the area under the curve. But in multiple dimensions, it's much more complicated, especially if this integral has bounded values. And such example of the typical set is just as this fuzzy surface. So there will be some kind of area where more will be contributing in the middle, less in the parts of this will be a bit complicated. And generally, the point is that samples from the typical set will contribute to will quantify our distribution behavior. So that's the main idea, that generally, if we would sample from the typical set, then we would have information about the probability distribution. Because if all the probabilities in the typical set, so samples should come from the typical set to get us. And the issue is that this is a two-dimensional, so you'll be aware, this is a two-dimensional picture. In two-dimensional distributions, typical set will still contain a lot of around the mode. It's still not far away, but we cannot, those complicated geometries happen in higher dimensions which we cannot visualize here. So this is a conceptual situation, okay? Do not imagine that the typical set will be observable in this way in like 2D plots. Usually it will also contain a lot of around the maximum here, but the most important is that in higher dimensions it will be more spread. So the main point here is that expectations are very closely related to samples, because generally we can compute expectations using samples, and we can, as long as we can generate such samples in such way that the average of samples asymptotically converges to the expectation, then our sampling is correct. So if we are able to sample from the typical set, the average of the samples will be the expected value of what we want to compute. And that's the main point of what we wanted to do. So here, generally, as long as the samples are generated properly, the estimate of the expected value is behaving normally, as a normal distribution. Why? Because we have a central limit theorem situation here. Do you remember central limit theorem a bit? It generally said like this: sum of random variables from the same distribution approaches, this sum is normally distributed. So if we are sampling from the same distribution, the average of the values will have a normal distribution. So if it converges asymptotically to the expected value, then we will be located around the value, and this will be represented by generally we can show that there's a series expansion around the estimate of the expected value, that it will be normally distributed with an expected values of this estimator be located in the actual expected value, and the standard deviation will be given by a square root of variance divided by number of samples, with the part that is vanishing, that is dependent on n, which is vanishing for n at least 10. So generally we can approximate approximate our expectation with this value, knowing that the error of this approximation is inversely proportional to the square root of n and dependent on the variance of the function. Moreover, we can even estimate the Monte Carlo standard error, which is because what we are doing here is the Monte Carlo sampling. Monte Carlo standard error is given as by standard variance estimator, just by using the values of sample variance. So notice this dash here, this is a sample variance and this is a sample mean, and using those values we are able to estimate the Monte Carlo standard error, which gives us the absolute error, and relative error is given by division of the Monte Carlo standard error by the sample mean. Okay? So the relatively simple situation is that if we want to compute the if we are using samples from the distribution, we can compute expectations, which are generally is what we want to do, because that will give us all the information that we need of certain functions, which we'll see in a moment what kind of functions. And this error is quantified by as a normal distribution, which generally makes it simpler. Okay. Moreover, what is important, in order to ensure relative precision, we need to generate a lot of samples. So if we want our precision to be very small, that is that our error is, let's say, 1%, then we have to generate a lot of samples. It's inversely proportional to the square of the relative error that we are interested in. The number of samples grows very high. And generally, we will be computing certain functions that can be useful for us. First of all, moments and cumulants, probability of certain events. We will be computing histograms, because histogram is not only a plot but also is a statistic with certain properties. We will be computing also ECDFs, which is the empirical cumulative distributive functions, and we will be computing quantiles. So let's cover those in order. Moments and cumulants are generally a statistical function. Moments are, you should know, the most known moments, of course, are mean and variance. But also there are skewness, curtices, and generally there are certain statistics characterizing function of probability distributions. And there are also additional cumulants, which are very similar to moments, but like slightly different defined. We won't be working on them during this course. What is, however, more important are the probabilities. And probabilities will be something that we'll be computing in order to verify how probable is that certain value will lie in certain interval. And this is an important practical situation. For example, we want to know how large, what is the probability of, let's say, getting more than 100 zloty from the slot machine, for example, or other stuff like that. So generally, we will be wanting to get estimate of we will be interested in probability that certain values will be located in its area. So this is generally very, very simple. You should, let's say, associate it with simple results from probability theory that you've learned multiple years ago. That generally, in order to get a probability of event, we have to integrate the probability distribution on the interval, right? What is important is that the expectation, this probability is also an expectation, because this is an expectation of the indicator function. And expectation of indicator function will be computed as an average of the values of the indicator function. Remember, indicator function is a function that gives you 1 where you are in the interval or in the area or in the set, and 0 otherwise. So the expectation of the indicator function is, of course, average of all the values of the indicator functions. So in other words, it is the ratio of number of samples inside the interval divided by total number of samples. and it will be an estimate of probability. This is very simple, very practical result. Why? Because if we can generate samples, let's say, what is the probability that we get less than half? So we just count all the values less than half, and this is very simple, just programmatically to do, right? So this is the expectation, but this expectation is represented just by counting in this case. So this is very simple, and again, this is the practical result that we use. Monte-Carlo standard error in this case can be computed, which I decided to give you. Do not bother you with the entire derivation, you will find it in the notes when they will happen, finally. But generally, this Monte-Carlo standard error is inversely proportional to the number of samples and depends on the probability that is being computed. What is, however, important is that relative error is inversely proportional to the probability. So, if probability is very small, then the error will rise. That gives you a situation that, for example, you want your estimate of probability is, let's say, 1%, and you want to get you want to get a small standard error. Let's say you want to have a standard error of your probability estimate less than 5%. Then, so you want to know that it is 1%, but you need to have very much confidence that it's 1%. That's not 2%, that's not 3%. You want to even more to know that it's not 1.10%. It might be important, for example, in stock market computation, in multiple situations like this, right? That where you have such large volumes that even 0.1% are important. So if you want to be sure that the probability of event that your expected value is 1%, expected value is 1%, you want to be sure that it is not more than 0.09095 and no more than 0.01.05, otherwise is within 5% from 1%, right? Then you need to compute use over 49,000 samples. Okay? Because small probability here causes you to, and strict requirement for relative error causes you to get the very high requirement for number of samples. Okay? So if you want to have small relative error, for small probabilities, you need to have a lot of samples, which generally makes sense that you want to be sure that those rare events are rare, right? So that's why you need a lot of number of samples. Different thing is a histogram, or not really different, but similar, because histogram is a collection of probability estimates. We know the histogram as a plot, right? We just represent the bits, but histogram can be much more, because histogram can give us the estimate of the probability distribution entirety. In the discrete case, it will be simpler. In the continuous case, it's a bit more complicated, but generally is the task of probability estimation for each of the intervals. Each bin of the histogram is an interval we want to estimate the probability of, right? So in this case, we will be able to get the probability distribution that is happening here. And depending on normalization, the representation of L's is different. If we do not normalize, we just give counts, then it's really not a probability distribution estimator. However, depending on, if we want to assume that the integral is equal to 1, then we create a step-valued continuous probability density function. And okay, it can happen. However, if we consider each bin as a separate discrete event, it will then create the probability mass function. Histogram will approximate the continuous distribution with a discrete distribution, just like okay, bin 1 is one event, bin 2 is second event, bin 3 is, and each of them have assigned probabilities which have the same quantized standard errors, multicolor standard errors, as if computing the intervals. So again, in the small values of histogram, where there will be small values, the uncertainty will, relative error will be large unless we have a lot of samples in the entire histogram. A complement to the histogram is the so-called empirical cumulative distribution function. And this is actually a function which is the simplest way of defining ECDF is by code. Because this is a function that characterizes the entire sample. You just take all the values of your sample, x, you count them, their number, then you sort them, and then you count unique values. If all the values are different, because this was a real number, then you can drop this step. Generally, you assign to each of the samples the value, the sorted samples, the value of number of samples that happened before. So you just sum all of them. So you will get a function that assigns probabilities to values smaller than that. And again, in this case, this function is a collection of estimates on intervals. But those intervals are not bins, they are just all the values from the minimum value observed to the one that we are here at the moment. So we are collecting all the values of the function from the start to now. So this gives us the so those will be the error. We can quantize the errors estimate because this is a collection of interval estimates, but for growing intervals. On a histogram, we had individual intervals. In ECDF, we have growing intervals. So we will see in a moment how it looks like. Finally, quantiles. Quantiles is, let's say, an inverse to the problem of determining the probability of an interval. Because we want to find a point for which the probability of getting the to get a quantile p quantile, let's say for example 5% quantile, we want to find such point in our data set or in our distribution generally that is the value of for which the again this is that point that the probability of the interval between minimal value and this value is equal exactly to p. So this is a for example, p% quantile or 5% quantile if probability of this interval is equal to 5. So we need to find the point yp. This is the value of this quantile, the value for which the probability up to this point require, let's say, 5%. And as long as the number of samples, like for example, if we want to get median and we get exactly half even number of samples, then all the numbers less than this side, greater this side, this is the median, the middle point of the data set. In case of distribution, this of course relates to balancing appropriate integrals. So find the point for which the integral up to this point here. In the sampling situation, we just count the points. So we are looking for points. Unfortunately, in the situation when there does not exist a point that will split those 5% and 95%, for example, then we need to use some kind of interpolation to determine this point. And this usually can be done with linear interpolation otherwise, but you need to be aware that quantiles in such situation might have represent the point that is not present in the dataset. So quantiles numerically just compute the appropriate value, and that's and they approximate the quantiles of actual distribution. So we are talking about samples, but where to get samples? How to get samples from a distribution? And this is generally a problem, which we'll cover the rest of this lecture and the next one. There are two ways of generating random numbers. First one is the hardware random number generation, and second is the pseudo-random number generation. Hardware random number generation generally is an idea that you get some kind of analog circuit put into your computer, and this analog circuit generates noise. For example, it has a lamp in it, in a way of a semiconductor lamp, like in these old computers or audio amplifiers. And some of those lamps are very noisy objects. And there is a digital analog to digital converter that will get the values, and because of those noises, you will get random numbers. This is a very specific application with multiple problems, because converters introduce certain problems, digital processing introduces certain problems. The randomness of those lamps is also debatable, because there are some frequencies, some bands that's more complicated. So you can get that with filtering, remove some bands, but generally you get band limited noises, which is not pure random, but certain randomness is limited. Generally, very specialized applications, some in cryptography, some where that you really need this randomness to be unrecoverable. On the other hand, we have the pseudo-random number generators. So it's a computer program that will generate values that behave approximately normally. So it will be a formula that will generate as a sequence of numbers. Why sequence? Because it has to be random with respect to other numbers that generated from the number generators. So it will be, let's say, some kind of a dynamical system that just generates new and new numbers, and those numbers should, the sequence of these numbers should have a low autocorrelation. So you shouldn't be able to predict next values from the previous ones, because this randomness would be bad. Has a long period, because all generally discrete situations will start returning to certain values. So it has a long period and uniformly distributed quantiles of the numbers in the intervals, and it's usually 0, 1. The simplest way of creating a random generation is a so-called congruent recurrence, which is generates number as xn plus 1 equals to the axn plus c modulo m. Appropriate selection of a and c might be complicated. Usually there should be primes, and it generates you integers. Then you divide it by the maximum integer and you get the 0, 1 numbers. So congruent generators are very simple, and of course you can, observing enough samples, you are able to determine a and c and m. So having enough samples, so then you can predict next numbers. That's why it's important in cryptography to generate random numbers that are not easily reproducible, because if you are able to reproduce those numbers, then there are issues. And of course, all depends also on the initial value that you must select. This value is called seed. And currently, the most widely implemented random number generation is used by the algorithm for Mersenne-Twister, which is a very complicated algorithm of generating random numbers. There are better algorithms now, because there were shown certain methods of recovering the seed of the Mersenne-Twister, but generally it's still a very good algorithm, most practically used for computation. So you can generate numbers from it. And So we are able now to generate random numbers in the interval 0, 1. They are uniformly distributed. But usually we want more complicated distribution, right? And this is the point that you need to use some kind of options. And one of the options is using the cumulative distribution function. And this cumulative distribution function is, of course, a function that we've covered empirical one before, but generally for each distribution, it's an integral of the probability function. It's a function that for each number of from the range of arbitrary values assigns the probability between 0 and 1, the probability of it being larger than the previous one. And the inverse of probability of cumulative density function, not formally but for practical purposes, it's so-called quantile function. So it would be a function that takes values from 0 and 1 and assigns to them the values from the set that over which the probability distribution function is defined. And that's our point to get to the random number generation from any kind of distribution. Because in one-dimensional case, which we will be covering today for the rest of the day, if we generate a random number sequence between 0 and 1, uniformly defined, and then we applied those numbers to the sequence, to the quantile function, the sequence of value of quantile functions will be distributed as pi distribution. So using inverse CDF for the quantile function, and random number generator, we will be generating numbers from any scalar distribution. And this is great. The problems in multiple dimension is that the inverse does not exist. Because in scalar, this is one-to-one function, from scalar from some subset of real to 0 and 1. So you can, and it's monotonous, so you can inverse it. In multidimensional, cumulative distribution function is then defined on the n-dimensional function, and there's problems. So that's one way, the practical way that usually is being done in any kind of implementation of random number generators from certain distributions. To get a very simple approach, but to get any kind of distribution that is not necessarily defined by someone else, and we do not know the distribution, we can use the very simple idea which is called grid approximation. Which generalized looks like this, that we take our probability distribution function, we select a grid of points, we evaluate values of those points on those grids, and we treat this function by values of as a discrete distribution, which is value of the function that corresponds to the value of the entire function. So the grid works as a probability mass function that approximates the probability density function, and we just normalize the values, so the sum of all those values will sum to 1. And that's the general idea. You can, of course, do it from Bayesian computation by multiplying likelihoods and priors to get the posterior, and then normalize it, so solve the problems of probability of data that we have usually by proportionality constant, and then you can sample from this grid as from the different distribution. We will now cover a few examples so you can see how the sampling works and how those estimates, Monticolor estimate works and what's happening. We'll start with normal distribution because it's simple. Then we will transform the samples from normal distribution using a link function, a logistic function. And then we'll go to more complicated distribution with so-called heavy tails distributions. So the distributions for which there is a it's more likely to find values that are far away from the center of the distribution. And we start with the most capricious one of them, the Cauchy distribution. Then we move to the student t, but with small number of degrees of freedom. And finally, we go to the more degrees of freedom to get the student t with normal behavior. So starting with normal distribution, here we can observe something called a rolling mean. This is like this. The values in the darkest color here are the values that are the mean of all the samples up to this point. So it's a rolling mean. We are increasing the window and we are computing the mean of. Here we also have 1, 2, and 3 Monte-Carlo standard errors. So as you can see, starting from the beginning, we have large Monte-Carlo standard errors, right? And increasing the sample size, the estimate of the expected value, so the mean of it, is close to the actual value that we had here, right? Okay. And we have 1,000 samples here, so it is very simple, and it corresponds to generally our distribution, that those samples at the end look like they would be distributed by. The values are corresponding to the 1.25 normal distribution. The histogram of the sample. Here you can see the histogram that is including the errors. So here we see, of course, the values of the histogram in each point, so the number of the normalized number of beans, so estimated probability of it being each bean. And here you have the Monte Carlo standard error for each of those. So having the Monte Carlo standard error, you can see that the probability distribution should lie somewhere in this area, okay? Which corresponds well to the analytical result. We see here something happened, but generally it's not that different from, here's a 1 Monte Carlo standard error. If we would go to 2 Monte Carlo standard errors, that will be some problems. As you can see, we have some issues around the maximum. Values around the 0 were not well sampled from the distribution. However, when we switch to the comparison with analytical result, we had to do an additional rescaling. So we had to take an estimated bin probability and divide it by bin width. So it would give us the result in the same scale as the analytical probability result. As it is known with histogram, changing the bin width changes the representation of probability distribution. If bins are too large, the actually estimates of errors are not that high, because as you can see here, because the bin is wide, the probability being located in this bin is not that small. The probabilities are relatively large, so the errors are not that significant. Smaller bins, so smaller probabilities happening here, larger errors, right? Especially larger relative errors here, depending on the width of the bin. Okay? Understood? Great. ECDF, so the function that takes all the values looks like this. As you can see here, the function is also includes with certain uncertainty that comes from the Monte Carlo standard error. Depending on the width of the interval, those errors are, the biggest errors are generally in the middle, the more they are become less and less as we move to the edges of the interval. This is understood. We sample, getting more samples, get a better approximation of the expected value. We use expected values of just the expectation, so the identity function, but we could use any kind of other function, right? So we could use and it would work exactly the same way. So for example, we can get samples from the inverse logit. So we can put the random samples through the values of the inverse logarithm. So it will get our real numbers constrained to the interval of 0 and 1. And it works exactly like the same. We are computing the expected value of this function just by performing appropriate computation, right? So we are creating a rolling mean. The more samples we have, the expectation converges, but of course the result is constrained now. It is not between it's not allowing values outside of the realm of possibility. It doesn't take values, negative values, just values between 0 and 1. Which you can see in the histogram that getting all the samples at the end gives us shape that is of course most concentrated about the expected value of the average of those samples, right? Which again, here we are representing, and those blue bars represent the errors of the Monticolor standard errors. So this is how uncertain we are about our probability density estimation, which again, when rescaled, fits rather well with the probability density function derived analytically, which of course could be is being done by appropriate change of variables, which we covered last lecture. Okay, this is clear? Simple. Okay, so now we'll move to a more complicated distribution, which is a student t probability density function. Student t probability density function is a distribution that has a lot of practical use because of few reasons. First of all, this distribution is it comes into place in certain analysis of some more advanced random, let's say analysis of certain random trials. But also, this is a distribution that, which here we have a standard student without any issues, but generally, it is a generalization of normal distribution. The coefficient called degrees of freedom, which corresponds to a situation when you have discrete numbers of normal trials, characterizes how the function is similar to normal or not. If degrees of freedom approach infinity, then you get normal distribution. However, the more important aspect is when degrees of freedom are small, because in that situation, the tails of the distribution are heavy. That means that it is rather likely that certain extreme values can happen. This is very useful, for example, in cases of so-called all-clear robust regression, when you have data points that are sketchy. You are not sure that it's possible that the data point that happened in your analysis isn't something that was accidentally added, and you want to make your model that will ignore those, or let's use those data that are complicated. In case of normal distribution, it's always a problem. If you get a value that is very different from the previous ones, the normal distribution will be strongly disrupted. That's why, for example, the mean is very bad for, let's say, for surveys. If you get a mean value and you, let's say, a teacher is being graded by students through the surveys, and lots of them give them 5, and one gives 1, then mean is moved. The median, for example, will not move. And in student distribution models, by using student distribution likelihood, will be robust to that changes. So it's a very important distribution that has a lot of applications in multiple places. And depending on number of degrees of freedom, there are certain issues with mean and variance of that distribution. Because in case the expectation is less than 1 or equal to 1, especially in case equal to 1 is important because it's so-called Cauchy distribution. If degrees of freedom is equal to 1, then neither expectation nor variance exist. They are just undefined. In case if they are between, they are greater than 1, then in this form given, student's distribution has the, is centered in 0. So has its expected value is 0. However, if the degrees of freedom is between 1 and 2, the variance is infinite. So it has an expectation, but it doesn't have variance. And if degrees of freedom is greater than 2, then of course both mean and variance exist. And if degrees of freedom approach infinity, the variance approaches 1 and the entire distribution becomes a student t. It becomes a normal distribution, standard normal distribution, but with mean of 0 and variance of 1, which can generally be seen here. It can be inferred from here through the appropriate limits. So let's start with Cauchy distribution. Getting samples from Cauchy distribution shows that rolling mean doesn't help much. Rolling mean behaves very weirdly because even if it starts in the beginning to approach something normally looking, then it gets a large value that moves the rolling mean away, or rolling average, to the somewhere else. So it introduces large uncertainty because variance of the sample jumps, so estimator of the Multicultural error also jumps, and that will happen always, because even if you get some time of normal samples, then a jump will happen. A low probable but still probable sample of large value will happen, and those values will go. And unfortunately, increasing the number of samples even 10 times won't change that. There still will be jumps. There still will be those disruptions, which will cause that are related to the fact that there is no expectation. So the question is, does even central limit theorem hold in this case? And we can check that by evaluating how our estimator behaves. So we generally created a series of experiments of 1,000 samples, and we've tried to estimate the mean of this distribution with different seeds. And we've analyzed how, so our samples for our distribution were not the samples from the, our samples were not samples from the distribution, but multiple tries to estimate the expected value, which should be normal and isn't. If central limit theorem would hold, then this would be normal, but it doesn't, and it's not normal. So why? Because the mean is undefined, so we cannot estimate it. But are Cauchy-like distributions useless? No, they are not. Because while these functions are not Baranski. Wykład mam odzwonię. Okay. So generally, while expectation is not defined, the probabilities are defined very well. So if we, let's say, analyze the indicator function of -1, 0 interval, so we just count the samples, rolling samples, but that are in the interval 0, 1, then everything is very nice. The expectation, why? Because that function has an expectation. Only the distribution doesn't have expectation, but still we can estimate what's the probability of samples located in the -1, 0 intervals, because we just can count those samples. And those rare samples of large value do not influence our computation, because they are not different for us for computation of being located in the interval. Sample of -2 is not different from -1 million, right? It's just not in the interval. So those jumps does not influence our interval analysis in this case. The same happens for medians and stuff like that. So those are robust to such changes, and we can really estimate that such probability is around 25% with relatively small multicolor standard error, which you can compute from that. So we can still analyze such distribution, but not necessarily the expected value of it, of the random variable is useful for us. But expected value of certain functions of those are fair game and can work. If we go to the infinite variance case, so if mean exists, then, well, it looks much better, right? Because as we can see, it concentrates around the appropriate value of mean value of mean equal to 0, right? That we have. This is a case for 1.5 degrees of freedom. I know degrees of freedom sounds like something that should be countable, but it's not. It can be any number. It can be a real number, a positive real number, but usually not less than 1. Mean is well defined, so it converges to the mean, but we have still jumps. So jumps in uncertainty, and we did the same trick. So we sample multiple times to get multiple estimates of the mean on let's say 1,000 samples. Then, as we can see the histogram, it's not horrible, but the uncertainty is not that reliable. The Monticolor standard error is not a good estimator, not good measure of uncertainty of the expected value, because it's still connected to the variance, and the variance is undefined. But we can still use different kind of quantization to get the result. Finally, the last case of 3 degrees of freedom. So the distribution that has defined everything, we have no issues here. As you can see, everything converges nicely. So if everything exists, it exists, despite that it's not being a normal distribution. And central limit theorem can be visually confirmed that it behaves like normal distribution, right? Finally, let's discuss about the tail behavior, because the problem that we are having here comes from the aspect that we can get those large samples that when we are analyzing those expectations of our functions might be very difficult. And the heavy tail processes have significant consequences. They are happening in economicals, in markets. Those are situations that everything looks normally, but then bad. The black swan theory, the anti-fragility theory of Nicholas Taleb. Generally, one of the typical methods of modeling the heavy tails is so-called Pareto distribution, or in this case, generalized Pareto distribution, which allows the consideration of tails of distribution that can be heavier. So the probability happening there is heavier. And why we are interested in that? Because while we are not using these models to estimate our data, we can use the estimator of k hat, so the coefficient of that distribution, as a tool to verify if something is sketchy with our sample. So we are using results from the frequencies probability theory just to evaluate how our functions will work, and using just data from the tails. So let's say we just remove the samples from the middle, let's say one plus minus one mean from the sample. Then we can evaluate the tails and see are those tails safe or not safe. And there is and we just separate it for the left and the right tail, because distribution can be asymmetric. Generally, if it is a diagnostic tool that says us if for our sample that we are interested in, k hat is greater than 0.7, there will be problems. Probably nothing can be computed. If it's less than 0.25, it should be okay. Those are general guidelines of happening. It can even get negative or something like that, but that's not a problem really. The issue is that it just doesn't get above 0.7. And if we consider our examples from before, we can see that for Cauchy distribution, in a smaller sample it can be very large. In the small samples it's approaches 0.75. For student T with small number of degrees of freedoms but still greater than 1, it is between this in this undetermined spot. So we have that it's not terrible, but there might be issues. And for 3 degrees of freedom we have very small value of k hat, which is getting a negative in case of normal, which makes sense because, as you can see, for 0 it becomes exponential distribution and the normal vanishes even faster than that. Summary. Just from what you should remember from this lecture, that Monte Carlo sampling, as long as okay, it will give us good estimates and certainly quantification of the samples. And that's how the probability computation work. We will be sampling and using those samples in order to get expectations. So everything that we will be doing from now on will be computing of some kind of expectations, explicitly or not, with some kind of errors. And of course, if there will be problems, there will be issues. We can diagnose that through Monte Carlo standard errors, which might be large, or through the k-hat distribution, k-hat's test function. So we can get some information can be computed. But the main problem is that at the moment it was very easy because we had one-dimensional distribution. So those distributions, even more, we've used distributions that are implemented. So there are functions that are computing samples from that. That's great. Unfortunately, when we get multiple dimensional, then we need something else. We need to generate samples in some clever way that will explore the typical set and generate our data in a proper way, and we won't have any issues with that. And for that, we will be using Monte Carlo Markov chain algorithms, which we'll cover on the next lecture. Thank you very much. Are there any questions? Okay, thank you.